A force acting at a point is theoretical concept. In space diagram or in free body diagram, when you show a force acting at one single point, then it is really speaking theoretical representation of a force which is acting at certain area. There is nothing like force acting at a point. Force acting at a point, also called a point force, is a theoretical concept. When two bodies exert force on each other, then when two bodies in contact exert force on each other, then the force exerted by the two bodies on each other is distributed on area of contact. For example, here a man of certain weight is standing on a wooden plank. So what is the force exerted by the man on the wooden plank? So we may show this force in a space diagram in this way: magnitude, direction, it is downwards, and this force is shown exactly at a point. But is it really acting at one point? No. The weight of this man is distributed over the area of contact. So this is what we have shown, weight of the man on the wooden plank. This is theoretical representation. Now a force can be distributed in infinite number of ways. Infinite, that word I have used. Check here with this example, let's check. This man now is standing on one leg only. So its weight, his weight has not changed, but now that weight is distributed over smaller area because area of contact has reduced. Now when this man is sitting, it is the same force on the wooden plank. It is the same weight of the man acting on the wooden plank, but now area of contact is different. One more example, it is the same man sleeping on the wooden plank. So now his weight is distributed over much larger area. And in all these four cases, we show weight of the man as a point force on the wooden plank. So remember, in mechanics, we can replace distributed force by a point force. This is actually a resultant of the distributed force. This weight of the man is distributed and it is the resultant of that. And that point on which that force is acting or weight is acting, we have shown, it is really point of application of the resultant force. So what you have learned from this example, a force can be distributed in infinite number of ways. A distributed force in mechanics can be replaced by a point force. In reality, point force is a theoretical concept. In reality, forces are always distributed in nature. When the two bodies exert force on each other, the force exerted by the two bodies on each other is distributed over area of contact. But actually, in a syllabus, in this video, we are going to study only two standard cases of distributed forces. Uniformly distributed force, one of the two standard cases of distributed forces. Uniformly distributed force or UDL, uniformly distributed load. In the space diagram, a uniformly distributed force is shown in this manner. What you should understand from this diagram, try to understand. On a 5 meter length, a force is distributed uniformly. Height of this load diagram represents intensity of loading. Intensity of loading means load or force per meter length. So what is total load on 5 meter length? 200 into 5, that is 1000 Newton. Given diagram, in space diagram, if uniformly distributed load is shown, then it is associated with its length and intensity. But now most important thing is, When we draw space diagram to analyze a problem on statics, remember, we always replace the distributed force by point force. We always replace the distributed force by point force. And that is what you are going to study in this video, how to replace distributed force by point force. So try to understand. As a single point force, how we should show this force in space diagram, check here. Draw the given length of the load diagram, length AB, which is 5 meter. And at center of its length, show the force. In this diagram, this rectangular diagram, direction is already mentioned. Matlab, it is downward force. So it is a downward force. Then magnitude. My suggestion is you compare it with area of a rectangle. So base into height, 5 into 200. So 1000 Newton. So 1000 Newton downward force. So this entire distributed load is actually a point force 1000 Newton downwards. Then point of application. Do you remember 3 parameters: magnitude, direction and point of application. And how we define point of application? Using distance from a reference point. But here when it is UDL, since it is very standardized distribution, length of this uniformly distributed force is 5 meters. So half of its length, that is 2.5 meters from left or 2.5 meters from right. So two things, remember, at center of the length, how to replace UDL at center of its length, and magnitude as if you are finding area of rectangle. There is one more method to show UDL in space diagram. The first diagram and this diagram suggest you the same thing. It is associated with its length, which is given 5 meters, and a notation is used on one of the sides of this line AB. This notation suggests you that it is uniformly distributed load and its intensity is always given to you, and it is a point force. How to replace UDL? At center of its length, and magnitude of the force 200 into 5. Don't forget to insert dimensions. Point of application of load is defined using dimension or distance from a reference. Now it is the same example. This is a UDL. What is direction of the force? And here there is possibility of confusion. So try to understand now. Since this is standardized notation, universally accepted notation, the direction of this force is associated with this notation. Check on which side of line AB this notation is used, and from that side push type of force. So here this notation is used above line AB. So from above it should be push type of force. This is how we identify direction. Watch here. Now you will understand it better. Here it is a UDL. On which side of this line this notation is used? From that side it is push type of force. Now I am telling you how we should identify direction. You know that it is at center of its length. Magnitude, as if you are finding area of rectangle, base into height. Height means intensity. But how to identify direction I am telling you. Watch here. And now you will understand it better. On which side of line AB this notation is used? From that side push type of force. On which side of line AB this notation is used? From that side push type of force. Be sure you have understood how to show direction of the UDL. It is to be shown at the center of its length. But on which side of line AB this notation is used? From that side push type of force. As I have told you, there are two standard distributed forces we are going to study in this video. One, uniformly distributed force, UDL, that was what we have studied just now. And the second type of distributed force is uniformly varying force. In short, it is called UVL, uniformly varying load. How it is shown in space diagram? Check. So its outlined shape is a triangle. It is always associated with its length, and height height of the load diagram is intensity. Here height of the load diagram is 0 and at end B height of the load diagram is maximum. That is, maximum intensity is always mentioned in the diagram. It is 200 Newton per meter. But of course, this intensity means height of loading is changing from 0 to maximum. It is uniformly changing. So when you watch such a diagram, immediately you realize that it is UVL acting. Uniformly varying load is acting. So how to show it as point force? Try to understand. In space diagram, first of all, show the length of the load properly. Magnitude, as if you are finding area of triangle, 200 into 6 divided by 2. Basic logic is average intensity into length. But to remember, my suggestion is you compare it with area of triangle, base into height by 2. So 200 into 6, height nothing but intensity, 200 into 6 by 2. Direction downwards is already known. How come 2 meters? Now I am telling you about point of application. So compare it with a triangular plate. Center of gravity of homogeneous triangular plate lies at a distance h by 3, b by 3. So from this vertical edge of the triangle at distance 1/3 of its base, so 1/3 of 6. That is why I measured 1/3 of 6, 2 meters from end B. And here at this point we should show that load 600 Newton. Once again listen, a triangular load, that is a uniformly varying load. How to replace it? By point force. So listen, magnitude as if you are finding area of triangle, height into base by 2, so 200 into 6 by 2, 600 Newton. Direction, that will be associated with the triangle itself, so downwards. And most important point of application, it is 1/3 of its length from maximum intensity end. So remember, there are only two types of distributed forces we are going to study in this syllabus. UDL, uniformly distributed load, and UVL, uniformly varying load. So remember, point of application for UDL, center of its length. For UVL, 1/3 of its length from maximum intensity end. And how to find magnitude of the loads? As if you are finding area. If it is UDL, use area of rectangle. If it is UVL, use area of triangle. It's simple. Here it is a trapezoidal load. Its intensity is varying from 10 Newton per meter at its end A to 25 Newton per meter at its end B. What we are having is simply practice of replacing distributed force by point force. Watch what we do here. We divide this trapezium into two standard shapes, a rectangle and a triangle. What you should understand from this diagram now, this trapezoidal load is combination of a rectangular load and a triangular load. Rectangular load means UDL and triangular load means UVL. So divide the given distributed force in standard shapes. So what is intensity? Remember, in case of load diagram, height of the load diagram is nothing but intensity. So intensity here means height of load diagram here is 10 Newton per meter. So watch here, total height is 25, it should be 10 plus 15. 10 plus 15. So simply we have divided this trapezium into two standard shapes, a rectangle and a triangle. That means in this given diagram there is a UDL as well as UVL. And now you replace distributed force by point force. So there will be 2 point forces, one with reference to this UDL and the other one for triangular load. So check for how we show point forces. Length AB is 6 meter. Focus on this triangular load. Tell me this triangular load, where is point of application of this triangular load as a point force? So 1/3 of its length is 6 meter, 1/3, that is 2 meters from maximum intensity. So this is a point of application of the triangular load. And how much is the triangular load? So height 15, base 6 divided by 2, as if you are finding area of the triangle. Height 15, base 6, height by base by, so 45 Newton. Now rectangular portion of the load. Total length is 6. How to replace UDL by point force? At center of its length. So total length is 6. So half of the length is 3 meters. So this is center of length AB. Downwards, that direction is already available in the diagram. And magnitude, as if you are finding area of rectangle 10, that is height of the rectangle. Check here. It is 10 into 6, 60 Newton. Try to understand. Only two types of distributed forces we are going to tackle. UDL and UVL. Rectangular load and triangular load. Important thing is there can be distributed forces in given question. But to solve problem, when we draw space diagram, in the space diagram, there will be no distributed force, because we always replace distributed force by point force. And this video was practice of replacing distributed force by point force. If required, if you are confused, go through this video once again. It's very easy to replace UDL and UVL by corresponding point forces. Thank you.